Hello viewers, this is Wagadaru now taking you through the story of A-level applied mathematics. And this video I'm going to talk about a topic of equilibrium of rigid bodies. So this topic is in mechanics and is suitable for students in both senior 5 and senior 6. So for rigid bodies in equilibrium, we must ensure that there is no resultant force acting, and that is translational equilibrium, and also we must ensure that there is no turning effect about a point, that is rotational equilibrium. So for a rigid body, you must ensure that there is no translational equilibrium by getting the resultant force and it will be equal to 0, and also ensure that there is no rotational equilibrium, and that is by taking moments. So that means that anti-clockwise moments must be equal to clockwise moments, so that when you add, the effect cancels out. So the resultant moment must be equal to 0. So because there is moment, let's see the formula for moment over force. So moment over force is given by the formula that moment about a pivot, so pivot is the point where I take moments from, is given by the formula FD sine theta. So this formula is very vital, and we shall use it more frequently in this topic. So what is F, what is D, and what is theta? So F is the force, and that force has to be in newtons. If it is not, you have to convert it. For example, if it is in kilonewtons, you have to convert it to newtons. Then D is the distance from the pivot to the point where the force originates from. So know that those two words, the distance between the pivot and the force where the point where the force originates from. So getting this value of D is what disturbs most students, so you have to know how to get D. Then theta is the angle between the force and the rigid body. So the theta is the angle between the force and the rigid body. So it's not any angle. You must ensure that angle you are using is between the force and the rigid body. So if these three parameters are got, then you can get moment from this formula. So this topic of equilibrium of rigid bodies can be subdivided into 4 parts. 1 is ladder problem, 2 is hinged rods, and 3 is jointed rods, and 4 is suspended rods. So these 3 will be covered in this video, and this last one will be covered in the next topic, since they have the same concepts. So now we shall start with the first part, which is ladder problem. So the situation of a ladder resting, know this word resting, against a wall with the foot of the ladder on the ground gives rise to a variety of problems. So what does that mean? It means that these variety of problems can be that the wall is rough or smooth, or the ground is rough or smooth. So the wall may be rough or it may be smooth, as also may the ground. So the ground can also be rough or smooth, and also the ground may be horizontal or not horizontal. It should be remembered that where the ladder rests against a smooth surface, there will only be normal reaction at that point. So when they talk about, like we said, it can either be rough or smooth, but in the cases where it is smooth, what should come in your mind is that only normal reaction exists. However, if the surfaces in contact are rough, what does that mean? It means that there is also frictional force, which acts parallel to the surfaces in contact and in the direction opposite to that in which the ladder would move. So know that whether the frictional force acts parallel to the surfaces in contact and also in the direction opposite to that in which the ladder would move. So when you know these two, then this topic will be easier. When the ladder is smooth, only normal reaction. When it is rough, there is both normal reaction and frictional force. We shall see how those forces are got. So note that if the ladder is uniform, so most questions they'll say that the ladder is uniform. So that means that the center of gravity is located at the midpoint. And remember, weight acts at the center of gravity. However, if they mention that the road is non-uniform, it means that the position of the center of gravity must be given. So they have to locate for you where the center of gravity is. That is, if it is non-uniform, but most cases it will be uniform. So we shall see both cases where the ladder is uniform and also where the ladder is non-uniform. So we shall start with case 1. There are 3 cases. One is when the vertical wall is smooth and the horizontal ground is rough, and also when they both are rough, the vertical wall is rough and the horizontal ground is rough, and also when both are smooth, whereby the vertical wall is smooth and the horizontal ground is smooth. So let's start with this case 1 where the vertical wall is smooth and also the horizontal ground is rough. So what does that mean? So let's first draw those walls, the vertical and the horizontal. Then next we shall draw a ladder which rests on both, inclined at an angle theta to the horizontal. So AB is our ladder. Now if this ladder is uniform, then the position of the center of gravity is at the midpoint, and that means that that's where the weight will act. And remember, weight acts vertically downwards. So this statement shows that C is the midpoint, AB and SC. So SC is half of AB, meaning that point C is the midpoint of AB. Then if this is theta, it implies that this will be 90 minus theta, because when you elongate this line, it will form a right angle triangle here, whereby this is 90, and implying that this balance will also add up to 90. So mg is the weight of the ladder. Then next we know that this ground is rough, meaning that it will have normal reaction. So this r is the normal reaction. Normal means perpendicular, that's why you see this angle is 90. But because it is rough, it will also have frictional force. Now remember, we said frictional force acts in the direction opposite to that in which the ladder would slide. So if you look at this ladder, if it is to slide, this part would shift going this direction. Therefore, friction must oppose the direction by going in that direction. Now this mu r is the formula for friction, whereby mu is the coefficient of friction and R1 is the normal reaction at this point. As you can see, this is normal reaction and this will be the coefficient of friction. So when you multiply the two, you'll be able to get the frictional force at that point. They also told us that the vertical wall is smooth. What does that mean? It means that only normal reaction exists. So that is why there is this normal reaction. So these two normal reactions are different. So that's why we distinguish them by this one being R1 and this one being R2. Then this and this are alternating angles, meaning they will be the same. So basically, that's how you can show the forces acting on a ladder resting on a smooth vertical wall and a rough horizontal ground. So with that knowledge, we can go and try out some questions. So question 1 came from UNEB 2004, paper 2, question 15, and says a non-uniform ladder. So know this keyword, non-uniform ladder. AB 10 meters long, so the length is 10 meters, and mass 8 kilograms, lies in limiting equilibrium with its lower end A resting against a rough vertical ground. Know that word, rough vertical ground. And this upper end B resting against a smooth vertical wall. If the center of gravity of the ladder is 3 meters from the foot of the ladder, and the ladder makes an angle of 30 degrees with the horizontal. I think realize that because the ladder was non-uniform, they have given us the position of the center of gravity. Then they say find the Roman 1 coefficient of friction between the ladder and the ground. Then Roman 2, the reaction at the wall, and they give it 6 marks. So the first thing to do is to make a sketch of the force diagram using a ruler. So we shall start with the vertical walls, vertical and horizontal ground, vertical and horizontal ground. Then next we shall show a ladder resting and inclined at 30 degrees to the horizontal. So this is the 30 degrees to the horizontal, and this AB is the ladder. The next is to locate the position of the center of gravity and put the weight of the ladder. So they told us that SC is 3 meters and AB is 10 meters. So 10 meters is the length of the ladder and 3 meters is the position of the center of gravity from the foot. That means that the weight always acts vertically downwards, and it was 8 kilograms, meaning it will be 8g. So this was 30 degrees. Like I told you, this forms a right angle triangle, meaning that these two angles must add up to 90. Therefore, 90 minus 30 gives you 60, which is this angle. The next is to show normal reaction at the foot. That it will be R1. Because this ground is rough, there will also be frictional force, as we already saw in the previous example. But for the vertical wall, there will only be normal reaction. And this angle and this angle are alternating, meaning they will be equal. So basically, that is the sketch of the force diagram. Next is to take moments. So we shall take moments about point A, meaning point A is our pivot. So we have to remember the formula for moment. That moment is FD sine theta, where F is the force in newtons, D is the distance from the pivot to the point where the force originates from, and theta is the angle between the force and the ladder or the rod. So in this case, if I want to take moment about this point, I have to, first of all, I have to find out, is the moment clockwise or anti-clockwise? Then next is to remember that any force whose line of action passes through the pivot has 0 moment. So if I stand here, if I use this as my pivot, it implies that this force has 0 moment, so I'll cancel it off, and this force has 0 moment because their line of action passes through the pivot, as you can see here. So we are left with this and this. So if I stand here, this force will give me a clockwise moment, and when I stand here still, this force will give me an anti-clockwise moment. So 8g is anti-clockwise and R2 is clockwise. So when taking moments, you have to remember that anti-clockwise moment is equal to clockwise moment. So in this case, this clockwise moment and this anti-clockwise moment must be equal. So let's start with the clockwise moment. So for clockwise moment, we have R2. Therefore, the formula is FD sine theta. So F is R2, which is this. Then D is the distance from the pivot up to where the force originates from. So distance AB is 10 meters. That is why we put 10 here. Then sine theta. Theta is the angle between the force and the ladder, and that is 30 degrees. So that is, in the end, we shall come up with R2 times 10 times sine 30 degrees. Then this side it will be anti-clockwise moment. So still we use the same formula, FD sine theta. So F is this 8g, then D is the distance from the pivot to the point where the force originates from, and that is SC, which is 3 meters, and that's why you write here 3. Then theta is the angle between the force and the ladder, which is 60 degrees. So in the end, you shall come up with 8g times 30 sine 60. So we have taken moments. Next is to substitute for g, because we know that in math 2, g is 9.8, and that means that we have only one unknown, which is R2. So when I make R2 the subject, R2 will be equal to 40.8378 newtons for the small places. Now before I go to the next slide, let's see how much can be awarded for this slide. So B1 is for the correct force diagram drawn using a ruler, M1 is for taking moments here, and A1 is for the reaction. So remember, in this question, they ask for reaction at the wall. So this R2 is the reaction at the wall, so we have answered Roman 2. Now we shall go to Roman 1, where they wanted the coefficient of friction between the ladder and the wall. So that coefficient of friction is this mu which they want, this mu. So now that you have taken moments, next is to resolve vertically and horizontally. So when I resolve vertically, I'll come up with R2 being equal to 8G. So where is that coming from? So when you look at this, because this is in equilibrium, it implies that upward forces are equal to downward forces for vertical components. So this is an upward force, R2, and this is a downward force, 8G, meaning this must be equal to that. So that is where this statement is coming from. But I know that G is 9.8, so I'll come and substitute for G as 9.8, and then I'll come up with 78.4 newtons. So that is when I resolve vertically. What if I resolve horizontally? I'll come up with mu R1 is equal to R2. So let's see where that is coming from. So because it is in equilibrium, it means that horizontally, forces to the left are equal to forces to the right. So if you look at this diagram, this force is to the right and this force is to the left, meaning they have to be equal. Therefore, this is where this statement is coming from. Now, next is to substitute for R1 and R2 and remain with mu as the only unknown. And when I make mu the subject, I'll come up with mu as 0.1732. So, coefficient of friction has no units, and basically that's what they wanted. So, for Roman 2, I just said because we already calculated it in the previous calculations. So now let's see how much can be awarded. So B1 for getting R1, M1 for resolving horizontally, A1 for the coefficient of friction. So that has been case 1, where the vertical wall is smooth and the horizontal ground is rough. Now we shall go to case 2, where the vertical wall is rough and the horizontal ground is also rough. So we shall start by drawing the vertical wall and horizontal ground. Then now that we shall show our force, our ladder. Then if this is uniform, it implies that the center of gravity is at the midpoint, and that's what this statement means. So mg is the weight of the ladder. So we shall start by also show the normal reaction at the foot, which is R1, and because this is rough, there will also be friction in the direction opposing the direction in which the ladder would slide. So if this point is to slide, this point will go this side, therefore the friction must act in this direction, as you can see it here. So that is for the foot. What about for the vertical wall? Vertical wall will also have normal reaction, and that is R2, but because it is also rough, it will have frictional force acting in the direction in which the opposite to that in which the ladder would slide. So if this point would slide, it would move downwards, meaning friction has to act upwards, as you can see it here. So mu2 is the coefficient of friction between the ladder and the vertical wall, and mu1 is the coefficient of friction between the ladder and the horizontal ground. Then R1 is the normal reaction at the ground, and R2 is the normal reaction at the vertical wall. So basically, those are the forces which should be shown in the case where the vertical wall is rough and the horizontal ground is also rough. So with that knowledge, let's go to this question. So question 2 came from UNEB 2005, paper 2, question 16, and it says a uniform. Now this time they have told us uniform, meaning the center of gravity is at the midpoint. So a uniform ladder of length 2L and weight capital W rests against a vertical wall with one end against a rough vertical wall, so the vertical wall is rough, and the other end against a rough horizontal surface, so the ground is also rough and horizontal. The angle of friction at each being arctan a third and arctan a half. So that means that the coefficient of friction, this one corresponds to the first, which was, because of this word respective, it means that this one corresponds to the vertical wall and this one corresponds to the horizontal ground. What does that mean? It means that the coefficient of friction for between the ladder and the vertical wall is a third, and that between the ladder and the horizontal ground is a half. Then part A says, if the ladder is in limiting equilibrium at either end, find theta, the angle of inclination of the ladder and to the horizontal. Then part B says, a man of weight 10 times that of the ladder begins to ascend it. How far will he climb before the ladder slips? So the first thing to do is to make a sketch of the force diagram. So for part A, we shall first show the vertical and the horizontal ground as we have seen before. Then next we shall show the ladder. They told us that the ladder is inclined at an angle theta to the horizontal, so we shall put there theta, and AB is our ladder. Then they told us that the ladder is uniform, meaning that the center of gravity is at the midpoint, and the weight, they told us it was W. The length AB was 2L, meaning SC will be a half of it, which will be L. The next we shall show normal reaction at the horizontal ground and also frictional force at the horizontal ground. Then also we shall show normal reaction on the vertical wall and friction at the vertical wall. So this angle and this are alternating, that's why it is they are equal. So basically those are the forces. Now let's start answering. So they told us that the friction at the vertical wall is a third and that on the horizontal ground is a half in the question. So we shall start by resolving horizontal. Remember, it's in equilibrium, meaning horizontally forces to the right are equal to the forces to the left. So this force is to the right and this is to the left, so they will be equal. So we shall say R2 is equal to mu1 R1. But we know mu1 is a half, therefore we shall come and say that R2 is a half that, implying that R1 is 2 R2. What about resolving vertically? Vertically means that upward forces are equal to downward forces. So upward forces, there is R1 and there is also mu2 R2, and they are equal to downward forces, which is capital W. So shall come and say mu2 R2 plus R1 is equal to W. But I know that mu2 is that and R1 is that, so I come and substitute. Then I make R2 W the subject to come up with 7 over 3 R2 is equal to W. So you have resolved vertically and horizontally. Next is to take moments. Now before we take moments, let's see how marks can be awarded for this slide. So B1 for the correct force diagram drawn using a ruler, M1 for resolving horizontal and simplifying, then another M1 for resolving vertically and simplifying. So now we shall take moments about A. When you take moments about A, this is what you are going to get. So we have to remember where the formula comes from. So the formula is FD sine theta. So let's see how it is used to get these values. So let's start with the one for this, mu2 R2 times 2L sine 90 plus theta. Where does it come from? So this force, mu2 sine 2, mu2 R2 is this. Therefore, that is the force. Then you remember the formula is FD sine theta. Now D is the distance from the pivot to the force point where the force starts from. So this force starts from here, meaning the distance is AB, and that AB is 2L. The next is to get the angle between the force and the ladder. That this angle, remember, the whole of this is 90, so the whole meaning that this will be 90 plus theta. So that is why where the mu2 r2 times 2L times sine 90 plus theta is coming from. So we have got this one. Now let's go to this, and remember the moment is also required. Remember, we have clockwise moment equal to anti-clockwise moment, so that means that when I stand here, I also have to get the moment when I stand here. At this point, this force will cause a clockwise moment, and also this force will cause a clockwise moment, but this one will cause an anti-clockwise moment, and these ones will cancel because they pass through the pivot. Therefore, we are going to add these two for clockwise moment and equate them to this for anti-clockwise moment. So now let's go to the one for R2. So for R2, it also starts from here, meaning that the distance from the pivot to this point where it originates from is AB, which is 2L, and the angle between the force and the ladder is theta. Therefore, the moment will be R2 times 2L times sine theta. So that is where this is coming from. R2 times 2L sine theta. What about this for W? So for W, this is the force and it originates from point C, meaning the distance from the pivot to point C is SC, which is L, and the angle between them is 90 minus theta. Therefore, the moment will be W times L times sine 90 minus theta. So that is where this is coming from. That's where this is coming from. So now that we have known how this step comes about, next is to substitute. We know that we have to substitute and simplify. We know that mu2 is a third, and we also know that from trig identities that sine 90 plus theta is cos theta, and we also know that sine 90 minus theta is also cos theta. So we shall substitute for that. Next is to realize that R2 is common, so we are going to cancel. When I cancel this, this, and this, I'll come up with this step, because 2 times a third is 2 over 3, then cos theta is there, then 2 sine theta is there, then here there is 7 over 3, which is that, and cos theta, which is there. Now next is to collect like terms. When I take this one this side, it will be 7 over 3 minus 2 to come up with, I'm going to take this one because the one which has cos, so I'll take this 2 over 3 cos theta this side to come up with 7 over 3 minus 2 over 3, which gives me 5 over 3 cos theta. Then this side I remain with 2 sine theta. The next is to divide, to take this cos this side. When I divide sine theta by cos theta, I'll come up with tan theta. Then when I take this one this side, I'll come up with 5 over 6, which is there. Now next is to use the calculator to come up with the value of theta, and that will be 39.8056 degrees. So basically that was the inclination they wanted. So M1 is taking moments, taking these clockwise moments, and M1 for taking the anti-clockwise moment and equating the two. Then A1 is for the required angle. So that was part A. Part B, they told us that a man whose weight is 10 times that of the ladder ascends the ladder. So what we do, we have to draw another sketch because the weight has changed. So the vertical wall, horizontal ground, and also the ladder is there. So the ladder is AB and inclined at theta. Remember, we have already got the value of theta, but for simplicity, let's first leave it as theta here. because it had a lot of decimal points. So next is to show the weight of the ladder, which is that, and also show the distance, and also show the weight of the man. So the weight of the man was 10 times that of the ladder. So if the ladder was W, his weight would be 10W. And he ascends up to a point D, so let this distance be X from the foot of the ladder. So this weight can be put anywhere. You can put this one either before this C or after C, anywhere, as long as, because this is a sketch, we don't know yet the value of X, and that is what we want to calculate. So next is to show the normal reaction, which is R3. Now the reaction has to change because the weight has changed. When the weight changes, reaction also changes. So previously this was R1, now it becomes R3. There should also be friction there. Then also here the weight will change. Previously it was R2, now it is R4, and there's also friction there. So now that is the sketch. Next is to resolve horizontally, resolve vertically, and also to take moments. So let's start by resolving horizontally. So horizontally means that forces to the right are equal to the forces to the left. So forces to the right, there is R4 only, and forces to the right, there is mu1 R3 only. So these two must be equal. That is where this is coming from. So the good thing, we know mu1 is a half. Therefore, when I substitute and make R3 the subject, it will be R3 equal to 2 R4. The next is to resolve vertically. Resolve vertically, upward forces are equal to downward forces. So upward there is this mu2 R4 and also this R3, but downward there is 10W and also W. So these two will be equal to the sum of these two, and that's where this segment is coming from. So the good thing, we know that mu2 is a third, so we shall come and substitute a third, and also know that R3 is 2 R4, so we shall come and substitute. Then this 2 is equal to 11W. So when I combine these two, I'll come up with 7 over 3 R4 equal to 11W, meaning that W is equal to 7 over 33 R4. So before we go to the next slide, let's see how much can be awarded for this slide. So B1 for the correct first diagram, M1 for resolving horizontally and simplifying, another M1 for resolving vertically and simplifying. So next is to take moments about A. Remember, taking moments, clockwise moment are equal to anti-clockwise moment. So let's see where these values are coming from. Let's start with the one for mu2 R4. So before taking moments, you have to know the pivot. So this is the pivot, and you have to look for the forces which cancel. This force cancels because it passes through the pivot, and also this one cancels because it passes through the pivot. So we are left with these two and these two. So when I stand here, this force will give me a clockwise moment, and also this one will give me a clockwise moment. But this one will give me an anti-clockwise moment, and also this one will give me an anti-clockwise moment. What does that mean? It means that the sum of these two moments will be equal to the sum of these two moments. So let's start with these ones which are clockwise. So for mu2 R4, it is a force. Then the distance is from the pivot to the point where the force originates from, and that is AB. And remember, AB is 2L. Then the angle is 90 plus theta. So the moment will be mu2 R4 times 2L times 90 plus sine 90 plus theta. So that is where this is coming from. Now let's go to this moment for R4. So for R4, the force is R4, then it also originates from point B, meaning the distance will be AB, which is 2L, and the angle between the ladder and the force is theta, meaning the moment will be R4 times 2L sine theta. So So that is where this is coming from. Now next is to go to this W. Let's see how that moment comes about. So for this W, the force is W, then the distance from the pivot, so this force originates from point C, meaning the distance is from the pivot is AC, which is L. And the angle between the force and the ladder is 90 minus theta. So the moment will be W times L times sine 90 minus theta. So that is where this is coming from. Next is this 10W. So for 10W, the force is 10W and it originates from point D, meaning the distance from the pivot to point D is X, AD is X. Then the angle between the force and the ladder is 90 minus theta, meaning the moment will be 10W times X times sine 90 minus theta. So that is where this is coming from. Remember, mu2 is 1 over 3, so you can come and put 1 over 3 there. Then sine 90 plus theta becomes cos theta, which is there. This one remains as that. Then for this one also, sine 90 minus theta is cos theta, which is that. Then also sine 90 plus theta is cos theta, which is that. So next is to divide throughout by cos theta. So when I divide throughout by cos theta, this term divided by cos theta cancels, so I remain with this alone, which is that. Then for this side, sin theta over cos theta is tan theta, so that is why there is tan theta here, and this other part is there. Then this side divided by cos theta, this goes away, so remain with WL. This side also, this goes away and remain with 10WX, which is there. Remember, my aim is to get the value of X. Now I remember that W is equal to 7 over 33 R4, so I'll come and substitute there. So when I substitute there, I realize that R4 is common throughout, so I'll come and cancel this R4, this R4, this R4, and this R4 to come up with this. Then next is correct like terms. So when I take this one this side, I'll come up with 2 over 3 plus 5 over 3 minus 7 over 33, everything over multiplied by L. So in the end I'll come up with 70 over 33L. Now next is to simplify. Realize that this is the same as this, so they cancel to come up with X equal to L. So that means that the man climbs a distance of L, and basically that's what they wanted. So now let's see how much can be awarded. So M1 is for taking moments clockwise and also anti-clockwise and equating the two. Then A1 for simplifying to get the required distance. So that has been case 2. Now we shall go to the last case of case 3, where the vertical wall is smooth and also the horizontal ground is smooth. So since you know the condition that when it is smooth on the normal reaction happens, there's nothing to write here, so we shall start with a question. So our question 3 came from UNEB 2000 paper 2 question 13, and it says the diagram below shows a uniform rod. So note this word uniform, meaning that the center of gravity is at the midpoint. Uniform rod AB of weight capital W and length L resting at an angle theta against a smooth vertical wall. I think this is there, that. The other end B rests on a smooth horizontal table. Note this word smooth and also smooth. Okay, the rod is prevented from slipping by an inelastic string. Inelastic means that it doesn't stretch. String OC, this is the string OC. C being a point on A such that AC is perpendicular to AB. I think you can see this angle 90 means perpendicular, and O is the point of intersection of the wall and the table. This is the point O. Angle AOB is 90 degrees. Angle AOB is 90 degrees. Find in terms of theta and W, Roman 1 the tension in the string, and Roman 2 the reactions at A and B. So the first thing to do is to redraw the given diagram, and after that we shall show the forces acting. So that is the ladder, then we shall show the weight and also show the string. So for this ladder, this angle is equal to this angle. These are corresponding angles. So this theta, if this theta, this is theta, and also this angle is equal to this angle because they are alternating. Then because this is smooth, only normal reaction happens, and that is the normal reaction RB at point B. Also, there is normal reaction at point A, which is RA. Then there is also a string preventing the ladder from slipping, and there will be tension in the string, so the tension is T. So not the directions, the direction of this tension matters. Why? Because if this string is being stretched, it will be pulled by forces like this and this, meaning that it has to oppose the direction. So this is the direction, so he decided to be in that direction opposite, and also here to be in that direction opposite for it to be in tension. Then also from geometry, realize that this, if this is theta, this angle will also be theta. So next is to find that we don't know the length SC, so let's first get SC. For you to get SC, we shall first use triangle AOB, and realize that cos theta, using this theta, is equal to adjacent over hypotenuse, that which is OA over AB. The good thing, we know AB is L, so in the end we shall come up with OA being equal to L cos theta. Now that we know OA, we can use triangle OAC. So AOC, this is a triangle, and with the triangle, when I use this angle and I want to get cos theta, it will be adjacent, which is SC over hypotenuse, which is OA. So cos theta is equal to SC over OA, but the good thing, I know OA, which is L cos theta, so L cos theta times cos theta will give me L cos squared theta. So now that I've got that, I can go ahead to answer the question. So I'll start by resolving horizontally. So when I resolve horizontally, forces to the right are equal to forces to the left. So forces to the left, I have to resolve this tension. Now there are two tensions, but our interests are the forces on the rod. So these are the forces on the rod. This force, we ignore it because it's on this wall. So for the forces on the rod, I'm interested in this tension, so I have to resolve this tension horizontally. I know that this angle is theta, the angle of the horizontal is theta, meaning that horizontal component of this tension will be T cos theta. Therefore, I'll come and say that RA is equal to T cos theta. What about vertically? Vertically, upward force are equal to downward force. So upward force is this RB, downward force, there is this W, and also a component on this tension, which will be T sine theta. So before we go to the next slide of taking moments, let's see how mass can be awarded here. So B1 for the correct force diagram showing all the forces which are remaining, then B1 for getting distance SC, M1 for resolving vertically, which is this, and this one for resolving horizontally. So next is to take moments about A. So when I take moments about A, I'll come up with these statements. So let's see where these values are coming from. Let's start with the force of RB. So for RB, I'm taking moments about this point, meaning that the force is RB, then this force originates from point B, meaning that the distance from the pivot to the point where the force originates from is AB, and we know that AB is L, so that is L. Then we also know that the angle between the force and the rod is theta, meaning that the moment will be RB times L times sine theta. So that is where this is coming from, RB times L sine theta. Then this W, let's see where those values are coming from. So for the first W, this force originates from this point, and this point is the midpoint. Remember, they told us that the ladder is uniform, so this is the midpoint. If AB is L, then this distance from A to this point will be a half L. So the moment and the angle between the force and the ladder is theta, meaning that the moment will be W times a half L times sine theta. So this is where these values are coming from, W times a half L times sine theta. Now let's go to the one of T. Now for T, first of all you have to realize that this angle is 90. So it originates from point C, therefore the distance from the pivot is SC, which is L cos squared theta. Then the angle is 90, which will give you, so therefore the moment will be T times L cos squared theta times sine 90. But remember, sine 90 is equal to 1, so in the end we shall remain with T times L cos squared theta. So that is where the T times L cos squared theta is coming from. Now the question is, why is it that this side there is only the moment for RB and this side there is moment for W and T? So the answer is on the type of moment. Is it clockwise or anti-clockwise? So when you go back to this diagram, you will realize that when I stand here, this being the pivot, this moment will give me a clockwise moment. This one will also be a clockwise, but this one will be anti-clockwise. Therefore, these two, the sum of these two moments will be equal to this moment. That's why RB is on one side and these two on the other side. So now next is to simplify. Remember, we already got under the part of resolving, we already saw that RB is T sine theta plus W. So we shall come and substitute for RB, which is that. Then next we shall realize that L is common, so this L will cancel, this L will cancel, and this L will cancel. So in the end we shall remain with that. Remember our aim is to get the value of T. So next is to expand. So when I open this bracket, I'll come up with T sine squared theta plus W sine theta. Then this side it will be the same, a half W sine theta plus T cos squared theta. The next is to collect like terms. So when I collect like terms, you realize that this one will go this side to become T cos squared theta minus T sine squared theta, which is the same as this T in brackets cos squared theta minus sine squared theta. Then when this one goes this side, 1 minus a half gives you a half, so in the end I'll come up with a half W sine theta. So next is to remember the identity for double angle, that cos squared theta minus sine squared theta is equal to cos 2 theta. Then with that I can now make capital T the subject, and to be W sine theta over 2 cos 2 theta. So basically that's what they wanted. Now let's see how much can be awarded. So M1 for taking moments and substituting for RB. Then M1 for double angle and B1 for simplified expression of T. Now we shall go to Roman 2. So Roman 2, they also wanted the reactions at A and B. So reaction at A, remember we already saw under resolving that RA is equal to T cos theta. Now that I've got T, I can come and substitute for T, which is that. Then I have to simplify. So when I simplify this and this gives me sine, then cos theta. Then I remember the double angle for sine theta, that sine 2 theta is equal to 2 sine theta cos theta. Therefore, sine theta cos theta is equal to a half sine 2 theta. Now that a half times this a half gives me this a quarter. Then that's why here there is sine 2 theta now, and this is cos 2 theta there, and this W still remains. So next is to remember that sine over cos, the same angle, gives me tan theta. So in the end I'll come up with a quarter W tan 2 theta. That is the reaction at A. What about at B? So at B, you still remember the resolved part was this. So when I substitute for T, I'll come up with that, then simplify to come up with that. So this and this gives me sine squared theta. Then I remember that double angle for sine squared theta is a half in brackets 1 minus cos 2 theta. So that a half and this a half gives me 4, which is there. The next is to put everything under one quotient by getting LCM, which is this. Therefore this LCM multiplied by this will give me 4W cos 2 theta. The next is to simplify this, and this gives me 3W cos 2 theta. So when I factorize out W, I'll come up with that. So basically that's what they wanted. Now let's see how much can be awarded. So M1 for this substitution and B1 for this expression for RA, M1 for this substitution, M1 for this combining to one quotient, and B1 for the final expression. So that has been ladder problem. Now we shall go to hinged rods. So in ladder problem, the ladder rests on a vertical wall and horizontal ground, but sometimes the body may be hinged to a vertical wall, hence the name hinged rod. So in this next part, we shall be having cases where the rod is hinged to a vertical wall, and in this case there will no longer be horizontal ground. Otherwise everything is the same, the procedure is the same as it was for ladder problem. You have to take moments and you have to resolve vertically and horizontally. So there being nothing to write, we shall go straight to the question. So question 4 came from UNEB 2008 paper 2 question 16, and it says a uniform beam. So uniform means the center of gravity is at the midpoint. So uniform beam SC of mass 8 kilograms and length 4 meters is hinged. So I think we realize that now we no longer use the word rest, we use the word hinged. At A, and is maintained in equilibrium by 2 strings attached to it at points C and D as shown below. So this is the diagram, this is the point strings D and C, and this is the hinge is at this point A. The tension in BC is twice that in BD. So note that tension in BC is twice that in BD. AB is 4 meters, AD is 3/4 of AC. Find part A tension in BC and part B magnitude and direction of the resultant force acting at the hinge. So we shall start by first drawing the given sketch. After that we shall show the forces acting. So let's start to show the forces. First we begin with weight as usual. So weight is it was 8 kilograms, mass was therefore weight will be 8g, and the length of the ladder was the length of this beam was 8 meters, meaning half of 8 will be 4. That is why here there is 4 meters. Then there will be tension in the string, so this will be in that direction, so the direction matters, and here there will also be this. Like I told you, when there is tension, it means that this rod makes the string to be pulled in this direction, therefore the tension has to be opposite. Also here in this direction, meaning the tension has to be opposite. So as long as the string is in tension, these should be the directions. We already saw that under the topic of connected particles, and it's available in the playlist. So that is string BD. What about string BC? String BC will have tension T2, and that will be that. So you don't know these inclinations yet, and you cannot resolve or take moments when you don't know these angles. So the first thing to do is to get those values for beta and alpha. So also another force is at the hinge now. So at the hinge now we no longer talk about friction because the beam is not resting, it is hinged. So what we do, we use other letters. We shall use X for the horizontal component and capital Y for the vertical component. So these are the two forces at the hinge. So when you combine the two, we shall be able to create the resultant force at the hinge which they want in Roman 2. So like I said, we can't resolve and we can't take moments when you don't know the values of alpha and beta. So let's first extract out the triangle for lengths so that we can easily get the values of alpha and beta. So we already know that SC is equal to 8 meters. Therefore we shall come and say that SC is 8 meters. Therefore AD, we are told that is 3/4 of SC, so it will be 8 meters. So AD is 8 meters. Therefore we can use SOHCAHTOA to get the values of alpha and beta, since these are right angled triangles. So when I use SOHCAHTOA for tan alpha will be equal to opposite over adjacent. So opposite is 4, adjacent is 8. That is 4 over 8, meaning alpha is 26.5651 degrees. For beta, tan beta is equal to opposite over adjacent, which is 4 over 6. Therefore beta is 33.6901 degrees. Then you also remember that T2 is equal to 2T1 because they told us that the tension in this BC is twice that in BD. So before we go to the next slide where we shall take moments and resolve, let's see how much can be awarded here. So here the only mark is for the correct forces in the diagram. So now we shall start by taking moments about A. So taking moments about A, we shall come up with that. So let's see where these ones are coming from. So you have to know moment of T1, T2 and 8G. So let's start with the one of T1. First of all, you have to remember that clockwise moment is equal to anti-clockwise moment. So that's the first thing to realize. So when I take moments about A, these forces will cancel because they pass through the pivot. Then this one, T1 will give me an anti-clockwise moment. T2 will also give me an anti-clockwise moment, but this 8G will give me a clockwise moment, meaning that the sum of these two moments is equal to this moment. Therefore for T1, remember, like I said, the forces we are interested in are the ones on the beam, so we are interested in these forces. These ones are not interested. So let's start with T1. For T1, it originates from point D. Therefore the distance from pivot is AD, and we saw that AD is 6. Then the angle between T1 and the rod is beta, which is that. Therefore, the moment for T1 will be T1 times AD, which is 6, times sine beta, which is 33.6901 degrees. So when you go back here, this is where this is coming from, T1 times 6 sine beta. Now let's go to T2. For T2, it originates from point C, meaning the distance is from the pivot is AC, which is 8. Then the angle is alpha, meaning the moment will be T2 times 8 times sine alpha. So this is where this is coming from, T2 times 8 sine alpha. Then lastly we shall go to 8G. So for 8G, this angle is 90, and we know that sine 90 is equal to 1. Therefore the moment will be 8G times 4. So that is where 8G times 4 is coming from. Now next is to substitute for alpha, beta and G. So we know that T2 is equal to T1, we are told in the question. So let's substitute 12 for alpha, beta and T2. So when I substitute, I'll come up with beta as that, alpha as that, G as that, and T2 as that. Therefore, when I make T1 the subject, I think we realize that T1 is the only unknown. So when I make it the subject, I'll come up with T1 as 29.9133 newtons. But remember, they want the tension in string BC, which is T2. So I'll come and remember that T2 is equal to T1, which gives, in the end, will give me 59.8266. So that was the tension in BC. Now next is to resolve vertically. They want the resultant force at the hinge. So we have to first resolve vertically and horizontally to get the values of x and y. Then we can use Pythagoras theory. So when I resolve vertically, I'll come up with y is equal to T1 sine 33.86901 degrees plus T2 sine 26.5651 degrees equal to 8G. So where are these coming from? Let's see where they're coming from. So resolving vertically means that upward forces are equal to downward forces. So downward force is only 8G, but upward there is this one, which is y entirely vertical, and this one is at an angle, meaning it has a vertical component, and the vertical component will be T1 sine beta, and this one also is at an angle, meaning it has a vertical component, which is T2 sine alpha. So when I add y plus T1 sine beta, which is that, then plus T2 sine alpha, which is that, will give me 8G. So that is where this statement is coming from. Next is to substitute for G and T1 and also T2, so that we have only y, which is only unknown, and in the end I'll come up with y equal to 35.0518 newtons. So before we go to the next slide, let's see how mass can be awarded for this slide. So M1 for taking moments and substituting for G, then B1 for tension in BD, and A1 for tension in BC. Then M1 for resolving vertically and substitution, and then B1 for getting the value of capital Y. So next is to resolve horizontally. So resolve horizontally, I'll come up with x being equal to T1 cos beta plus T2 cos alpha. Let's see where that is coming from. So horizontally, it means that forces to the right are equal to forces to the left. Now Forces to the right is only a capital X, but forces to the left there is this component which is T1 cos beta, and also this component which is T2 cos alpha. So that is where this statement is coming from. Now next is to substitute for T1, beta, T2 and alpha. So when I simplify, I'll come up with capital X being equal to 78.3999 newtons. So now that I've got the value of capital X and capital Y, I can come and get the reaction at the hinge, or the resultant force at the hinge. So horizontally it is positive, which is to the right. Vertically it is positive, which is upward. Therefore from start to end will be our reaction at the hinge. So when I use Pythagoras theory, I'll come up with my RA being equal to 85.8788 newtons. Then when I use SOHCAHTOA, I'll come up with tan theta being equal to opposite over adjacent. Therefore theta is 24.0889 degrees. Therefore the reaction at the hinge will be equal to this is that magnitude, and in the direction that. So basically that's what they wanted. Now let's see how much can be awarded. So M1 for resolving and substitution, B1 for the value of X, M1 for this substitution, Pythagoras theory, and A1 for the magnitude, M1 for attempting to find the direction, and B1 for stating. So this statement has to be seen for you to get this B1. So that was question 4. Now let's go to question 5. Question 5 came from UNEB 2007 paper 2 question 13A. So it says that a rod AB 1 meter long has weight of 20 newtons at its center of gravity, and its center of gravity is 60 centimeters from A. So that means that the rod was non-uniform. It rests horizontally with A against a rough vertical wall. A string BC is fastened to the wall at C, 75 centimeters vertically above A. Find part A, the normal and frictional forces at A. So I think we realize that when they talk about resting, they talk about frictional forces. If it's a hinge, they just say reaction. That's the only difference, otherwise they are the same as the ladder problem. So find the normal and frictional forces at A. Then after that they said, if friction is limiting, find the coefficient of friction. Then Roman 2, they want the tension in the string. So the first thing to do is to make a sketch of the force diagram. So first of all, they told us the vertical wall, and also that the rod AB is horizontal because it rests horizontally. So that is AB. Then there was a string fastened at this end B and to the vertical wall. So in this case, they told us that the center of gravity is 60 centimeters from A, meaning from A you measure 60 centimeters, which is 0.6, to come up with the point where the weight will act, and the weight was 20 newtons. It was given in the question. The next is to show the tension in the string. So those are the tension, that is the tension in the string. The inclination is needed for you to take moments and to resolve. We also have the force here, normal reaction, and also the friction. So friction is capital Y and normal reaction is capital X. But we don't know this inclination, so we have to first get it before we can take moments or resolve. So we know this distance was 75 centimeters, which is 0.75, and this AB was 1 meter. So this is a right angle triangle, meaning I can use Pythagoras, I can use SOHCAHTOA. So before I go to the next slide, B1 is for the correct force diagram. So now we shall use Pythagoras theory and get BC, which is 1.25 meters, and then sine theta will be opposite, which is 0.75 over hypotenuse, which is 1.25, and that will be 0.6. What about cos theta? Cos theta will be adjacent, which is 1, over hypotenuse, which is 1.25, and it will be 0.8. So now that I've got that, I can now take moments. So when I take moments about A, I'll come up with that. So let's see where that segment is coming from for T and for 20. So taking moments about A, it means that this A is your pivot. Now these forces cancel because they pass through the pivot. So and this force is not needed because it's for the ground, for the vertical wall. Our interest is this. Now there are two forces, there is this T and the weight. When I use this as a pivot, this force gives me an anti-clockwise moment, and this one gives me a clockwise moment, meaning this will be equal to this moment will be equal to the moment of this. Now let's start with the moment for T, capital T. For capital T, it starts from B, and distance AB is 1 meter. Then the angle between the rod and the tension and this or the force is theta. Therefore the moment will be T times 1 sine theta. So that's where this is coming from, T times 1 sine theta. Then for the 20, this angle is 90, meaning the moment will be 20 times 0.6. That is where 20 times 0.6 is coming from. So the good thing, I already know the value of sine theta, so I'll come and substitute for this here to remain with T as the only unknown. Therefore T is equal to 20 newtons. Also resolving vertically, I'll come up with that. So where is it coming from? Let's see where it's coming from. Vertical, remember, it means that upward forces are equal to downward forces. So vertically, there is this one which is entirely vertical. This one is at an angle, meaning it has a vertical component which is T sine theta, and also a horizontal component which is T cos theta. Now because we're dealing with vertical, we shall say y plus T sine theta is equal to 20 newtons. That is where this statement is coming from. So the good thing, we know the value of T and also the value of sine theta. So when I substitute, I'll come up with that. Therefore capital Y is equal to 8 newtons. So that means that frictional force is equal to 8 newtons. But remember, they also want a normal reaction, so we have to resolve horizontally. So horizontally, we shall come up with x being equal to T cos theta. Where is that coming from? So remember, horizontal, it means that forces to the right are equal to forces to the left. So forces to the right is this x, and forces to the left is this one, which is T cos theta. So they will be equal. But the good thing, we know the value of T and also the value of cos theta. So T is there and also cos theta is there. So when I substitute, I come up with x being equal to 16 newtons. So what does that mean? It means that now normal reaction is 16 newtons. Now that I have friction and normal reaction, I can get coefficient of friction. So coefficient of friction will be equal to frictional force over normal reaction, and frictional force is 8 and this one is 16. So when I divide the two, I'll come up with 0.5 as my coefficient of friction. So basically that's what they wanted. Now let's see how much can be awarded. So M1 for taking moments and A1 for the tension. Then this M1 is mobile, meaning it can be given at this point of resolving vertically or at this point of resolving horizontally. Then A1 for the frictional force, another A1 for the normal force, then B1 for the coefficient of friction. So that was question 5. Now we shall go to question 6. So for question 6 says a non-uniform rod, non-uniform meaning they have to specify the position of center of gravity. Non-uniform rod AB of mass 10 kilograms has its center of gravity at a distance a quarter of AB from B, not that word, from B. The rod is smoothly hinged at A. Now they've talked about the hinge. It is maintained in equilibrium at 60 degrees above the horizontal. Know that word, because previously we have been dealing with horizontal rods. Now this one is inclined at an angle of 60 degrees to the horizontal and above the horizontal by a light inextensible string tied at B and at right angles to AB. All those points are worth noting. Calculate the magnitude and direction of the reaction at A. So the first thing to do is to make a sketch of the force diagram. So we shall start with the vertical wall. Then we shall put the ladder which is inclined at an angle of 60 to the horizontal, AB. Then we shall put the string which is at right angles with the ladder. So that's why this angle is 90. And this is 60 from geometry, because this angle is also 60. So next is to put the weight. So the center of gravity was a quarter AB from B, meaning it is towards B. And the mass was 10 kilograms, meaning the weight would be 10 G. Because this angle is 60 degrees, it implies that this is 30 degrees. The next is to show the reaction at the hinge, split into two components, horizontal and vertical. So horizontal is capital X and vertical will be capital Y. The next is the tension in the string, so it will be capital T. So basically those are the forces. Now let's see the working. So we say that they didn't give us the length of the uniform rod, so you shall let it to be small l. That means that distance SC is equal to 3/4 of AB, because BC is a quarter AB, meaning that the remaining part is 3/4, which is 0.75 L. Now taking moments about A, when I take moments about A, what you should realize that these forces will cancel because they pass through the pivot and I remain with this and this. So for this, remember, clockwise is equal to anti-clockwise. So for this tension, when I stand here as a pivot, this moment will be anti-clockwise, but this one will be clockwise. So this moment, this T starts from B and AB is L, and this angle is 90, meaning it will be T times L sine 90, but sine 90 is 1, meaning that's why you remain with T times L. For the 10G, it starts from C, meaning SC is the distance, which is 0.75, and the angle between the force and the rod is 30 degrees. Therefore, the moment will be 10G times 0.75 L times sine 30. So when I substitute for G, L cancels first of all. I remain with T as the only unknown, because G is 9.8, therefore my value of T is 36.75. So before we go to the next slide, let's see how mass can be awarded for this slide. So M1 for the correct force diagram drawn using a ruler, M1 for taking moments anti-clockwise and also clockwise and equating the two, then B1 for tension. So next is to resolve vertical. When I resolve vertical, I'll come up with y plus t cos 60 degrees equal to 10g. So let's see where it comes from. Remember, resolving vertically, it means that upward forces are equal to downward forces. Therefore, upward, this y, capital Y is entirely vertical and it's upward, but this one is at an angle, meaning part of it is vertical and part of it is horizontal. The vertical component, because the angle is lying on the vertical, it means that the vertical component will have cos. Therefore, it will be t cos 60 degrees, and the horizontal will be t sine 60 degrees. Therefore, in the end, when I resolve, I'll have this y plus t cos 60 degrees equal to 10g. So that is where this segment is coming from. So when I substitute for t and for g, I remain with capital Y as the only unknown. And when I make it the subject, it will be 79.625 newtons. That was resolving vertically. Next is to resolve horizontally. Horizontally, we shall have x equal to t sine 60 degrees. So let's see where it comes from. So this x is entirely horizontal. Remember, horizontal, it means that forces to the right are equal to forces to the left. So forces to the right, there is only this capital X, and forces to the left, there is the component of this tension, which will be t sine 60 degrees. So that's where this segment is coming from. But the good thing, I know the value of t, and I know, therefore when I substitute, I'll come up with x being equal to 31.826 newtons. So now that I have the values of x and y, I can get the magnitude of the reaction from Pythagoras theorem, and it will be equal to 85.7498 newtons. Then the direction will be arctan of y over x, which will be arctan of this over that, which gives me 68.2135 degrees above the horizontal. So basically that's what they wanted. Now let's see how much can be awarded. So M1 for resolving vertically and A1 for the value of capital Y, M1 for resolving horizontally and A1 for the value of capital X, M1 for substituting using Pythagoras theory and A1 for the magnitude, M1 for attempting to find the direction and B1 for stating the direction. So this statement has to be included above the horizontal. So that has been hinged rods. Now we shall go to freely jointed rods. So in hinged rods, the hinge was between the rod and the vertical wall, but sometimes the hinge may be between two rods. So in that case, we call them jointed rods. So there is no difference between hinged rods and jointed rods, but under hinged rods, the hinge was between the vertical wall and the rod. It was one rod and the vertical wall. But in jointed rods, it means there are two rods which are hinged together at a common point. So there's nothing to write. Let's get started with our question. So question 7 came from UNEB 1997, paper 2, question 15, and says two uniform rods AB and BC of masses 4 kilograms and 6 kilograms respectively are hinged at B and rest in a vertical position on a smooth floor. So smooth floor means only normal reaction exists. A and C are connected by a rope. So this is the rope. Part A, find the reactions between the rods and the floor at A and C. The reaction at A and the reaction at C. When the rope is taut, taut means tight. In other words, being tight. And tight means there is tension in the string or the rope. Then part B, if now a body is attached a quarter way up CB and the reactions are equal, find the mass of the body. So this is the good thing here, they have given us the sketch. So next is to show the forces in that sketch diagram. So let's do that. So we are going to first redraw what was given. So the weight here acts vertically downwards, and this is the midpoint. So the mass was 4 kilograms, so the weight will be 4g. This side, the mass was 6 kilograms, and the weight will be 6g, also act vertically downwards and at the midpoint. Then also, because it was smooth, only normal reaction occurs at A, so that will be RA, and also here only normal reaction occurs, and that will be RC. Then because this string is tight, there will be tension here to be in this direction and here to be in that direction. When the string is in tension, those should be the arrows pointing towards each other. So those are the forces. Now we have left out one force, and that's the reaction at the hinge, because these are two reactions, but they are equal and opposite. One is that side and another is that side. So for you to show these reactions, you have to split these two rods, as we shall see in the next example. But in this example, it does not require splitting because they didn't ask for tension. If they had asked for tension, we would have split the rods. But since they didn't ask for tension, we are not going to split, and therefore we are not going to show the reaction at the hinge. So you just leave it as that because they counterbalance each other. So we are going to resolve forces vertically. So vertically, realize that upward forces are equal to downward forces. So this and this are upward, then this and this are downwards, meaning that this sum is equal to this sum. Therefore, RA plus RC is equal to 4G plus 6G. When I simplify, I'll come up with that equation, RA plus RC being equal to 10G. What about taking moments about A? So when I take moments about A for the whole system, I'll come up with that statement. So where is it coming from? So in this case, there's no way you can get these angles, but the good thing they told us that the rows are uniform, meaning this is the midpoint. So if you are given this as 4, then the midpoint is from here to here, which is 0.02. Then also if the whole of this is 8, then the midpoint is here, which is 0.04. Therefore, for 4G, this 4G, that is the first, and the eventual distance is from here up to here, which is 0.02, half of this. But for 6G, this 6G, the distance is from here up to here. The good thing, we know that from here up to here is 0.04, and from here to here is half of 0.08, which is 0.04. That's why you see here 0.04 and 0.04. So this 0.04 is for this, and this one is for that. So those are the forces which are clockwise, because when I stand here, this moment will be clockwise, and also this will be clockwise. But this one will be anti-clockwise, so it will be on the other side. And this tension will have zero moment because it passes through the pivot, and also this one will have zero moment because it passes through the pivot. So this side, it will be RC times 0.04 plus 0.08, because from here to here 0.04, then from here to here 0.08. So next is simplify. When I simplify, this gives me that, and this gives me that, and this gives me that. Then this and this gives me this. Then after that, I remember that G is 9.8, so I substitute for G and remain with RC as the only unknown. Therefore, RC will be equal to 686 over 15 newtons, or you can round off to 45.7333 newtons, and is okay. So now that I've got RC, I'll come back to equation 1 and say that from equation 1, when I substitute for RC, I remain with RA as the only unknown. Therefore, I'll come up with RA being equal to 784 over 15 newtons, or you can round off to 52.2667 newtons. So basically, those are the reactions they wanted in part A. Now let's see how marks can be awarded. So B1 for the correct force diagram, M1 for resolving vertically, M1 for taking moments clockwise and anti-clockwise and equating the two, A1 for the value of RC, M1 for this substitution, A1 for the value of RA. So now they told us that if now, that is part A, now part B, if now a body is attached a quarter way up CB and the reactions are equal, find the mass of the body. So that means that we have to draw another force diagram to show that information. So for part B, let's draw another force diagram. So we shall start by showing the weights, that is 4G and that is 6G. Then this is another body of mass M. Let the mass be M, so it was attached a quarter way up. Then the reaction, they told that they are equal, so this it will be R and yet will be R because they are equal according to the question. Then the tensions, the string is in tension, so the arrows must be pointing each other. As you can see them here, when the string is in tension, the arrows must be pointing each other. So now shall we resolve vertically. When I resolve vertically, upward forces there is R plus R, and downward there is 4G plus 6G plus mg, which is that. So when I simplify, I come up with R being equal to that, because this will be 2R. Then when I divide by 2, I come up with R being equal to 5G, because this 10G divided by 2 is 5. Then this mg divided by 2 is 0.5 mg. So next is to take moments about A. So when I take moments about A, I'll come up with that. So this 4G still, the potential distance is half of this, which will be 0.02. That's where this is coming from. For 6G still, it will be from here up to here 0.04, like we saw in the previous in part A. Then from here to here is 0.04, that gives you 0.08. Then for mg, they told us that this is a quarter way up. So from here to here is a quarter, and a quarter of 0.08 is that. So the whole of this from here up to here is 0.12, because 0.04 plus 0.08 is 0.12, but you have to subtract off the quarter to remain with the distance from A up to that point. So that gives you 0.12 minus 0 minus a quarter, which is 0.02. For R here, the whole of this distance, like we said, it is equal to 0.12, so it will be R times 0.12. So next is to simplify. The whole of this will give me that, then this gives me that, and this gives me that. Remember, my aim is to make M the subject. So when I substitute for R, remember R is this, so I come and substitute there, come up with that, and when I open brackets, I come up with that. Then collect like terms, I come up with that, then make M the subject will be 1 kilogram. So the body was supposed to be of mass, is supposed to be of mass 1 kilogram. So basically that's what they wanted. Now let's see how mass can be awarded. So B1 is for the correct force diagram, M1 for taking moments here and also here. Then M1 for substitution of R, A1 for the value of M. So that was question 7. Now we shall go to question 8. Question 8 came from UNEB 1995, paper 2, question 6, and it says, two uniform rods AB and SC, each of weight W and length 10 centimeters, are smoothly hinged at A. the ends B and C rest on a smooth horizontal plane. An inextensible string joins B and C and the system is kept in equilibrium in a vertical plane with a string taut, meaning there is tension in the string. An object of weight 2W climbs rod AC to a point E such that AE is 8 centimeters. Given that angle BSC is 2 theta, determine in terms of W and theta Roman 1 the reaction at the ends B and C, and Roman 2 the tension in the string, and hence show that the reaction at the hinge A is given by W over 10 square root of 49 tan squared theta plus 4. So the first thing to do is to make a sketch of the information given. First of all, we have rods AB and also rod SC. They have a string attached to points B and C, which is that. So the angle BSC was 2 theta, meaning it is, remember these rods are symmetrical because this same length, same weight, meaning this angle will be divided into 2. So the weight of this will be at the center, which will be W. Remember the length was 10, so it will be 5. Then same applies to this rod. W, the weight was W and length was 10, so it will be 5. The next is a body of weight 2W, which was put here so that AE is 8. So from here TI is 8 centimeters. The next is the reaction. So this will be only normal reaction, which is RB, and also here to be only normal reaction, and that is RC. The next are the tension. They have to point towards each other. So those are the values. So from geometry, this angle is equal to this angle, corresponding angles, and also this is equal to this alternating angles. Similarly, this is equal to this corresponding angles, and this is equal to this corresponding angles, and this is equal to this alternating angles. So now for the whole system, we are going to take moments about point B, about this B. So first of all, you have to look for the forces which cancel. This cancels out, and this one also cancels out. So you're left with the rest. So when you take moments, you come up with that, whereby clockwise moment is equal to anti-clockwise moment. So clockwise moment is equal to anti-clockwise moment. Therefore, this W is a clockwise moment. This one is also clockwise moment. This one is a clockwise moment, but this one is anti-clockwise moment. Therefore, let's start with W. W, it starts from this point, which is 5 centimeters from the pivot. Pivot is here. So the force is W, which is that, and the distance is 5, and the angle between the force and the rod is theta, which is that. Then we shall go to another W. This one, the force is this. Then the distance is from here TI is 10, and from here TI is 5. That is why we have here 10 plus 5. And the angle between is theta, which is sine theta there. Then for W, from here TI is 10, and from here TI, like we said, it was 8 because it was given the question. So that's why you see here 10 plus 8, and the angle between is theta. Then for RC, from here TI is 10, and from here TI is 10. Therefore, that's why you see here 10 plus 10, and the angle between is theta. So with that, we have taken moments. Next is to simplify. So when I simplify, I'll come up this. Remember, sine theta is common throughout, because so this sine cancels with this, and that. So we remain with 5W here, 15W there, 36W there, and 20 RC there. Therefore, when I make RC the subject, it will be 14W over 5. So reaction at C is 14W over 5. Next is to resolve vertically. Resolving vertically means upward forces are equal to downward forces. So upward forces we have this and this. Then downward forces we have this, this and that. So when I equate the two, I'll come up with that. But I know RC, therefore RB will be equal to 6W over 5. So basically that's what they wanted. Now let's see how mass can be awarded. So B1 for the correct force diagram, M1 for taking moments, and also M1 for taking another moment. So this is clockwise, the other one is anti-clockwise, and equating the two. Then A1 for the value of RC, M1 for resolving, and A1 for value of RB. So that was the part of Roman 1 of reaction at ends B and C. Now we shall go to tension in the string, and lastly the hinged part, which is reaction at the hinge. So when they ask for tension in the string, we have to split these two rods so that we can easily show these tensions differently and also this reaction differently. So let's see how that is done. So with that we have split them, therefore the tension will be split and also the reaction will be split. So let's start with the weight as it was previously, and also here weight as it was previously. Then also this other additional weight of 2W as it was previously. No more reaction. Now we already calculated it and it was this. And also here we already calculated the reaction and it was that. Now the tension will be split into two. One T will be on this rod and another one will be on this other rod. Then here still no more reaction. It is split into two. One will, if this is vertical, this side it will be, if this is upward, this will be downward. And also here, if this is to the right, this will be to the left. So that's what it means by splitting the two rods. So now we can take moments for rod AB only. So for AB only, when I take moments, I'll come up with that. So I'm taking moments about A, so I'll start, this will be my pivot, meaning this force cancels and this force also cancels. So I remain with these others. So for this one, it originates from point B, meaning distance AB is 10 centimeters. That is why there is 10 here. The force is this, which is there. Then the angle between the two is theta, that is why there is theta there. Then we shall go to capital T. Capital T, it originates from point B, meaning the distance is 10 centimeters, that is why there is 10 there. Then the angle between the force and the rod is 90 minus theta, that's why it is there. The next is W, this W, the force. Then the distance from pivot is 5, that is why there is 5 there. And the angle is theta, that is why there is theta there. So basically that's how they take moments. So next is to simplify. I'll come up with that. So before we go to the next slide, let's see how mass can be awarded. So M1 for this moment and M1 for this other moment, clockwise and anti-clockwise. So next let's see how we can simplify to get the tension. So when I simplify, I come up with that. Therefore, T will be equal to 7W times theta over 10. Now we shall go to the hence part. Hence part, we have to resolve vertically and horizontally. So vertically for rod AB, I'll come up with that. So when you go back, we shall see where that one is coming from. So for rod AB, vertically means upward forces are equal to downward forces. So upward is only this, and downward there is this and also this. So these two are equal to this. That is where this statement is coming from. Therefore, capital Y will be equal to W over 5. What about resolving horizontally? Horizontally we shall come up with X equal to T. Let's see where it comes from. So horizontally, you realize that this force is to the right and this is to the left, so they should be equal. But I know the value of t, meaning x is equal to 7w tan theta over 10. So now that I've got x and y, I can get the magnitude of the reaction at the hinge from Pythagoras' theory. Therefore, substitute for x and substitute for y, then simplify. So when I simplify, I'll come up with that. LCM is 100, so put everything under one LCM, which is 100, to come up with that. Then I realize that capital W squared is common. I'll pull it out. Then square root of W squared is W, so it can come out. And also square root of 100 is 10, so it can come out. Remain with only 49 tan squared theta plus 4 inside. And that is what was required. So basically that's what they wanted. Now let's see how much can be awarded. So B1 for simplified expression of capital T, M1 for values of y and x, then M1 for this substitution, B1 for simplifying the required expression. So that was question 8. Now we shall go to question 9. Question 9 says, two uniform rods, AB and SC, are smoothly jointed at A and have their other ends attached to supports at 2 points B and C. Now this word supports at the same level. Each rod has a mass of 50 kilograms and is inclined at 60 degrees to the horizontal. Find the action at the hinge. So the first thing to do is to make a sketch. So we shall look for two supports. So these are the two supports. One is support B, another one is support C. And they told us that they inclined at an angle of 60 degrees to the horizontal. That's why there is 60 here and 60 here. So we have split the two rods because they want the reaction at the hinge. So when they want reaction at the hinge, you have to split the two rods. So just start with the weight. Weight of this is 50 G, and this is 30 degrees because this is 60. So the length of the rod AB is 2L, meaning this will be LL. We have let it to be 2L. So this is also 2L for LL because they are uniform and the weight is still the same, 50 G. Then here, because these are supports, there should be reaction here at B and also reaction at C. And there should also be friction, which is F1 here, and friction here, which is F2. Then for this one, if this is upwards, this will be downwards. And for here, if this is to the right, this will also be to the left. So that's the first diagram, and that is 1 mark. So let's see how this first diagram is used. So taking moments about B for rod AB only, we shall come up with that. So let's see how this comes about for rod AB only. So for AB only, taking moments about B, this is a pivot, meaning these four forces cancel. So the 50 G, it's not grams, it is 50 G, Newton. The moment it starts at this point, which is a distance L from the pivot, so the distance is L, and the angle is 30 degrees. Therefore, the moment will be 50 G times L sine 30. What about X? So when you go to X, the angle is 60 degrees and the distance from here to here is 2L. So the moment will be X times 2L sine 60 degrees. And lastly, Y. So for Y, the angle is 30 degrees and the distance is 2L. Therefore, the moment here will be y times 2L sine 30. So next is to simplify. Sine 30 is a half, so a half times 50 is 25, and this g, that gives it 25g. Then sine 60 is root 3 over 2, so root 3 over 2, the 2 comes with this, we remain with root 3 alone, and this L, and this x, so the L's cancel this, and that. Then here sine 30 is a half times this 2 gives 1, so we remain with only capital Y. So that will be equation 1. Now shall again take moments about C for rod AC only to come up with that. So let's see where they come from. So moments about C for rod AC only, about this one. For this one, the angle is 30, meaning the moment will be 50g times L sine 30 degrees. Then for this one, the angle is 60, meaning the moment will be 2L times x times 2L sine 60 degrees. And for this one, the angle will be this, which is 60 plus 90, which will be y times 2L times sine 120. So sine 120 is the same as sine 60, so you come up with that from the quadrants. So next we simplify and come up with the second equation, which is that. So I've got two equations, I have to use them to get the values of capital X and capital Y. So before I use them, let's see how mass can be awarded. M1 for taking moments, B1 for equation 1, M1 for taking moments, B1 for equation 2. So we have to solve these two equations simultaneously to come up with values of X and Y, after which we can get the action at the hinge. So when I add equation 1 and equation 2, I come up with 490 is equal to 2x root 3, meaning x is equal to 245 root 3 over 3. I think realize that we have removed the surd from the denominator because the final answer must not have a surd in the denominator. So I have to rationalize to remove it from the denominator. Then when I subtract equation 2 from equation 1, I'll come up with y equal to 0. Now that I've got x and y, I can get action at the hinge being equal to this, because this is 0. So basically that's what they wanted. Now let's see how mass can be awarded. So B1 for the value of X, B1 for the value of Y, B1 for the action at the hinge. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on equilibrium of freely suspended bodies or particles. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on equilibrium of freely suspended bodies or particles has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.